Good evening, and thanks for joining tonight's TI Technology webinar hosted by Texas Instruments, where tonight we're going to take a look at some expressions and equations and how to teach them efficiently. My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough to teach, tough to learn concepts accessible to all my students. And tonight we're really lucky to be joined by our two panelists, Janice Mitchner and Scott Knapp. Janice has been a mathematics teacher for over 35 years, teaching courses from Algebra 1 through Calculus 3. She received the Presidential Award for Excellence in Science and Math Teaching, is an AP Calculus reader, and has been with the T-Cubed organization since 2003. Her passion is mentoring and training teachers on using technology as a tool to enhance learning. So Janice, thanks for joining us tonight.
I'm excited to be here.
And Scott is in his 22nd year of teaching high school math and currently teaches Algebra 1, Algebra 2, and AP Calculus AB at Glenbrook North High School in Northbrook, Illinois, a suburb of Chicago. Scott is an AP Calculus reader and has been a T-Cubed regional instructor since 2011 and has led numerous workshops on the TI-Nspire graphing calculator, as well as served on authoring teams for the TI-AD4 and TI-Nspire professional development. Scott enjoys presenting sessions at local, regional, and national conferences on how to use technology to support student success in learning mathematics. Scott, thanks for joining us tonight.
Thank you so much, Mike, and hello to everyone out there.
And Scott, will you discuss the agenda for tonight?
Yeah, I'll just give a brief rundown of what we're planning to do. I'll be starting off tonight talking a little bit about factoring and solving or simplifying some equations to solve to help make students see some equivalents and connections. And then Jan's going to jump in with converting some radicals to exponential form and vice versa, and also some interesting things on composite functions as well. And then at the end of the night, we'll be having a webinar drawing to hand out a handheld of your platform choice to the winner.
Awesome. Thanks, Scott. And Jan is going to discuss our expected outcomes.
Tonight, we're going to leave here with saying I can leverage technology to demonstrate equivalent expressions from a graphical, numerical, and algebraic perspective. And I can encourage students to be more efficient when working with expressions and equations.
Thanks so much, Jan. Scott, let's get this party started. Feel free to share your screen.
All right, sounds great. Thank you so much, Mike. So as I was introduced there, I kind of have an interesting year in front of me because it's the first time where I'm actually teaching all the way from algebra through calculus in the same year. I've been an AP Calculus AB teacher for about 8 years. Algebra 2 has kind of always been my other course, and then this year I'm also in Algebra 1. So it's brought me some interesting perspective, as well as just thinking about, okay, now that I'm back to teaching the foundational level, what is it that I want to do to prepare them for that middle course of Algebra 2 and eventually to be able to take some sort of calculus course. So this was really interesting to put together this webinar and to just kind of process where I'm at in my own journey with my students. So as I mentioned, I'll be talking about factoring tonight and creating equivalent expressions through factoring, as well as doing some work with simplifying equations. And both Jan and I think you're going to find are going to be looking at things as the calculus teacher, wanting to have just a graphical view, a numerical view, and an algebraic view of what we're looking at. And we're going to use the technology and leverage it to show ways to motivate that with our students. In the end, I hope that through the concept of equivalence, that my students become a little bit more efficient in the work that they do, and then ultimately a little bit more effective in what they do. So that's kind of where I'm going to go tonight, and so I'm going to go ahead and jump in and talk about some factoring. I'm going to begin with just a simple idea because I'm about to teach factoring in Algebra 1. It comes, I think it's our next unit actually, starting in a couple of weeks here. Which of the following expressions is equivalent to x squared plus 6x plus 8? And for many of our students, this becomes a pretty simple exercise in factoring, but I wonder how mechanical it is to them, and do they really realize what they're doing when they're factoring and the idea of equivalence and how they're actually creating an equivalent expression that's connected by multiplication that, as we know as math teachers, can then be leveraged for many different things. And many of those things we'll see tonight. So I thought, as I'm about to teach factoring in Algebra 1, what are some ways that I could help motivate that idea of equivalence for them to actually visualize that and experience that? So I'm going to pull up here my TI-84. And I actually did, one of the things that you can do in the actions is you can save an emulator state, meaning I can save something that I've already entered some equations into or expressions into, and then I can later load it. And I went ahead and did that tonight so that I can save some time from typing. And I put our initial expression in of x squared plus 6x plus 8, and then those 4 options that I showed. And each of those options you see involve numbers that multiply to 8 and also multiply to 6. And initially our students don't necessarily know how to factor, but again, what I'm trying to motivate here is what does the factoring actually involve and what does it produce for us, which is something equivalent. Now you're going to notice here that when I entered them, to the left of y2, y3, y4, and y5, I'm going to do it on y2 here. You see this little trace. I'm going to change the attributes of how it's going to graph. That way I have a little bit more time to kind of digest what I'm looking at on my screen. So to the left here of y2, I already changed them to nice different colors. You can change the color of what you're graphing, but you can also change the attributes from a line to a thicker version of the line. There's some inequality options that you have, and then there's this one that I call the trace, that it's actually going to slowly trace that graph. Because one thing I found is that once you hit enter and graph, a lot of times these expressions and functions graph so quickly that you may miss out on the math piece of what you're looking for. So when I press graph here, we see quickly that blue initial expression, and now it's starting to plot that second one. And I see here, I'm going to go ahead and pause it by hitting enter. That's one thing that you can do as well. I see that it's not a match, meaning it's not the equivalent expression to x squared plus 6x plus 8. But slowly graphing here in just a second is the magenta graph, y2 or y3, which was x plus 2 and x plus 4, and that is the match. And so we can see that graphically those two expressions are equivalent. Now this one's also kind of interesting. It's x plus 2 and x plus 3. It's almost a match, but not quite, and that could give you a nice piece of conversation to have of, well, why is it almost actually matching up? They're not equivalent, but they're close, and we can see that graphically. And if you think about what's going on with the two factors, that provides a nice discussion. And then finally in y5 was the other distractor that's not going to work, and we can see that that is also not a match. So right away with factoring here, this just gives students an idea of what you're doing is creating an equivalent expression, and we can see that graphically, which is one of our big views of a function when we get to AP Calculus. The second view I want to motivate students to think about is numerically, and that would be using a table. So one of my favorite features of the 84, at least in how it displays things, is the table feature. So I pressed second and graph to access my table. And the reason I really like this is the color stands out to me and I'm able to really see these values well. I'll kind of compare that to the Nspire maybe a little bit later, but I like the view of the table here on the 84 just a little bit better. And I set it up so x is just increasing by ones. And you could set it up to have it so that you can independently put in values for yourself. But I went ahead and just put in values from -5 to 5. And if we take a look here, it's showing the various outputs, the numeric outputs for each of those expressions. Okay, so if you take a look here, and I just saw that question come in, and I'll try to address that. And if any other questions come in, Jan knows that she can also stop me and pause as well. But we see here y1 is the column we're trying to match, and it doesn't take long to notice that it's not until we get to y3 that we match up output for output. Okay, and so again, y1 and y3, those two expressions are the equivalent ones. And if I slide over here, you can see that y5 isn't. Now, what's interesting is that if you take a look at when x is 0, y1, y2, and y3 are all the same output. And that could provide an interesting discussion as well, because even though the original expressions aren't equivalent, they are for certain x values. Okay, so again, a numeric view of this. Just coming back to that question real quick, those colors are determined by whatever color you've chosen to make the graph. So the reason why one was in blue and not, let's see, let's find something that's got a little bit of color, not yellow, is because I chose blue. Now if I come to the table, Y1 will be shown here in yellow. Okay? All right, now let me quit out of here and go to the calculator side because we've looked at how factoring creates expressions that are equivalent graphically and numerically, and then the next way I want to do that is algebraically. And I know this might seem tedious, but I think it might be really important, especially in Algebra 1, for students to realize what equivalence here means. So I'm just going to pick a number, 3.7. And I'm going to fill that into that first expression. Now let me just pop those up real quick so you kind of know what I'm doing here. Okay, I'm putting the 3.7 into my initial expression of x squared plus 6x plus 8. And then I'm going to do the same thing for the factored expressions and see when I get something equivalent. Because a lot of times I don't think that our students realize that that's what factoring creates. So when I put 3.7 into the original quadratic expression, I get out 43.89. Okay, so which of the expressions that I was given, if I put in 3.7, will also give me out 43.89? And we don't often have students fill values in to expressions that are factored, but I think that's an important thing for them to know is that they can do that, and they would end up with equivalent things if they had equivalent expressions. Obviously here, that first option, not equivalent. Okay, now I'm not going to test them all, but we know that the next option in line is going to be the one that works. I'm going to go up and highlight that line and press enter. That essentially is doing a copy and paste of that entry line. And then I'm going to go and just change the values to the new values for that expression, which was x plus 2 and then x plus 4. Okay, and we can see now that, okay, that is the equivalent expression. I ended up with the same thing. Now, why did I choose 3.7? You know, sometimes you got to be careful because like we saw in the table before, if x was 0, 0 is kind of a special number. You may end up tricking yourself into thinking things are equivalent. 3.7 probably isn't going to do that, and that's why I chose that. Another way we can do this, and again, I don't think I would do this very often, but just to show students what factoring does and how it provides equivalence, we could also use the function entries, the function rules themselves. And we can access those by pressing alpha and trace, and we get the list of options we have. Okay, and so if I take y1, and you're essentially using this as if it were function notation, and y1 of 3.7, I can see what I get out, and that's that 43.89. So what that's doing is actually what I calculated up here. And sometimes my students don't learn function notation until Algebra 2, so I don't know that I'd want to introduce that to them in Algebra 1 yet. I might save that for them in Algebra 2. Okay, now I'm just going to save a little bit of time because we know that it's in Y3, and so once I go to Y3 and I input 3.7, I find out that I end up with that same output. So again, showing algebraically here and with the function notation. Okay, one more thing that I want to show here before we start to look at some examples of how does this then play out from algebra to calculus. Why is this equivalence so important with factoring? Is one of the things I didn't know about is that the calculator actually can test out whether things are true or not. Okay, so for example, right now, if I type the number 5 and I go to second math and ask it, is 5 equal, and select that equals to 5, the calculator outputs a 1. And the meaning of that 1 is, yes, that's a true statement. Okay. Similarly, if I gave it a false statement like 5 equals 4, it would output a 0, meaning false in this case. So one thing I might do is, knowing that we have in y equals our original expression and then the different possible factored versions of it, is test out which of those expressions are equal. So if I press alpha and trace to access my entries, is y1 Second, math will allow me to get that equals. Is y1 equal to y2? And we know that's not true, and sure enough, the calculator returns a 0. And then if I go back again, I'm going to highlight it, copy it down. Is y1 equal to second trace, or sorry, alpha trace? Is that equal to y3? It's going to output a 1. Okay, and that means that those two are equivalent. So there's a variety of ways you can do this numerically, but in the end, if we come back to our original example, the idea is we want students to realize graphically we would see the same graphs if they're equivalent expressions. Numerically, we would see the same outputs for given x inputs, and then algebraically, whether we actually fill in and perform the algebra or use some sort of function notation, we can show that these expressions are equivalent and that x plus 2 times x plus 4 is the equivalent expression. Okay, so sometimes we don't realize how technology can really play that role in influencing something as simple as equivalence. And like I said at the very beginning, I don't want my students just to be mechanical about factoring. I want them to have a good understanding of what factoring creates for them. So now I have a question for you. I'm going to pause for about 30 seconds. I'm about to show you some examples from my recent classes of where this comes into play. Remember, I teach Algebra 1, Algebra 2, and AP Calculus. But where do you factor? Where are you factoring? Where would the idea of equivalence come into play in your classrooms? What topics? And so if you could just chat me a quick message, and I know some of you know the chat because I've seen a lot of chats coming in on the side. Where are your students needing to understand equivalence and factoring? Go ahead and chat me something.
Okay, we have like solving quadratics, polynomials.
Yeah, that's where I'm at too with quadratics. I'm about to come up to polynomials in Algebra 2. Okay, finding zeros, good. Distributive property.
Limits.
Okay, good, yeah. And we're seeing things from algebra to calculus. Obviously, factoring is a major tool. Maybe one of the biggest tools we want students to have is that idea of how to factor, but also what does it mean to be equivalent. So let me just show you some examples from my classrooms. So this is something that we did recently in Algebra 2. We also do a little bit of this in Algebra 1, but just simplifying a rational expression. Okay, the idea that factoring creates equivalent expressions, and then if we can reduce out common factors to be 1, that gets us the simplified version of that expression. But one thing until I started thinking about this webinar was I never go back. I'm not going to type these things in. I'm just going to show you some screenshots. But I never go back and graph the original and the simplified version to show that, hey, they do overlap. They are equivalent. Okay, and I never go back to that table and show that, hey, the two columns in the table are equivalent. Oops, except in one spot. When x equals 1, the initial expression has an error, but when x equals 1, the second expression doesn't have an error. But for everywhere else, those things are equivalent. Now, that's a good discussion point, right? And especially about the idea of having restrictions, restricted values in your domain. I never go back and show numerically that those two things are equivalent, or rarely do I. I certainly don't do it enough. And I think that we need to do that so that students, again, realize that what they've done is created something that's equivalent for most of the domain of what we're working with. In calculus, this just becomes something, that's just a small piece of evaluating a limit. We can't find the value of a limit of a function that's discontinuous unless we reduce out what's causing that discontinuity, and then we can evaluate. Okay, here's something that came up recently, right? I think it was the end of my first semester in calculus. Where are we increasing on f of x? We know that we need to find the derivative, and typically we factor them to find our critical values. But where do we test those critical values? We know we need to check their intervals that are created. So what if we want to test -5? Does it make more sense to test that in our original derivative function or in the factored form of our derivative function? And my students, again, maybe if they had Algebra 1 and learned from me that, hey, we can plug into the factored form to verify the equivalence, maybe they are already better equipped when they get to calculus to say, oh, we can plug into any of them if they're equivalent. let's go to that factored version because all we care about is the sign of the output. We don't care about the specific output, and that will get us there a little bit more efficiently. And then I love this one because one of the things my students sometimes neglect is their best friend in calculus, which should be algebra. And perhaps they may not be as close to algebra as I'd like. And sometimes they do a wonderful job of demonstrating a quotient rule, but in the end, when this becomes factored and we have some equivalent factors, we find out the derivative here is 1. But if we had just taken a little bit of time to look for something equivalent in that numerator, we could have saved a lot of time to find that derivative. Okay, so those are some examples of factoring and why that establishment of equivalence is so important, and again, from those 3 different views, graphically, numerically, and algebraically. Okay, I want to switch gears here now and talk a little bit about something somewhat related, but in a little bit of a different context, and that's simplifying equations from algebra to calculus. My students recently had to find zeros of this quadratic function, which they're coming to know that that just means y is 0. For a while they thought it was always x-intercepts, but I just introduced them to the world of non-real numbers, and so that definition came back to what it should have been for them. But a lot of them want to take something like this and factor it. And I'm thinking to myself, boy, if you just took one little step here, you could have something that's a little bit easier to work with. So one of the things I like to show them is I'm going to graph that function, and I'm going to use the Nspire this time and show off some of the capabilities of the Nspire. I'm going to open up a notes page, which is probably one of the least used pages that can do the most dynamic stuff. And I'm going to open up a math box on that notes page by pressing Control and M, and you'll see it opens up this little red box, and in there I'm going to type, and you can also access this through the menu, but I'm just going to save some time here. I'm going to type define, and I'm going to define the function f of x equals, and the function that I want to define the zeros for, 2x squared minus 8x minus 24. And if I press enter, the notes page tells me it has been defined. Okay. Now, something that's kind of new for the Nspire, if I go up and I am highlighting that math box and I press a right click on my computer, or control menu is the same thing as right click on the handheld. If I press graph, it will instantly pop open a split screen and I can see the graph of that function I just defined. That's kind of a big bells and whistles moment, I think, with the Nspire. Now, I'm going to go ahead and change my window up here a little bit. This is one of my favorite things about the Nspire window, is that I can change it on the screen. I don't have to leave the screen to go change my Xmin, Xmax, which I think is great because I can see exactly what I'm changing and how it updates as I change it. And so now I've got that function entered. And if we take a look, the places where y is 0 are x-intercepts. They're at -2 and 6. Okay? Now, in order to prove what I'm trying to show here, which is that I want to simplify that initial equation, I'm going to quickly insert here, by menu, insert, a slider. Okay? And most people don't necessarily associate sliders with a notes page. I'm not sure where that went here. Lost it for a second. Let me see if I can do that again. Menu, insert, and then I want the slider. There we go. And I'm going to call the slider A, and I'm going to start it from 1 to about 10 by ones. And I'm going to go ahead and go down here and minimize it. I usually like to minimize my sliders. And right now, if I press that slider, not much is happening because it's not attached to anything. Okay. Well, in my next line, I'm going to open a math box again, and I'm going to define a second function called g of x. And I want g of x to be f of x divided by that slider value. So I like to press Control and divide so that I open up that fraction template. And then I'm going to type f of x, and I'm going to put it over a. Okay? And so right now, it's defined that as a function. I can't really see what g of x is, so on the last, this is the last entry I'm going to do, I'm going to type g of x so that I can see that it's created that function for me. And notice now when I press my slider, it's dividing f of x by that value. Okay? All right, I'm going to plot this second function, and remember we did that earlier. If I'm hovering over that math box and I right-click, I can graph, and we now see that. Now here's something I'm not happy about, and I want to ask them if they can change it. I want it to be in a different color. They put them both in the Dodger blue. So I'm going to quickly come over here and just change the color on G there. Change it to be red so that there's some distinction between the two. Okay, and I'm also going to do one other thing. I'm kind of showing off a couple of the Nspire skills here that I really like. I'm going to change the attributes of that, and I want that, whatever that A value is, I want it to actually show up. So if I go down to where it says label parameters in the attributes, I'm going to click that to the right so that it's showing that, okay, it's dividing it by 1 right now. And here's where the magic happens, because if I press my slider, we see that the red function g of x I defined updates. It's being divided by some value, but notice my whole purpose of this is to talk about or show and demonstrate that those two x-intercepts are still at -2 and 6. It doesn't matter what variation of f of x I have. No matter what I divided it by, the zeros would still be in the same place. Okay, so the technology shows that we can actually simplify that expression when we're setting it equal to 0 and then solve, and we'll have the same solutions. So let me come back to my notes now. What I want my students to be thinking is, how about if I divide both sides of the equation by 2, and now I can factor and solve to find those zeros much quicker versus the stress of factoring something with a lead coefficient like 2. Okay, and there's a lot of places this comes up, and if you start encouraging your students to do this, you'd be surprised how often they do, and they look for this. Before I get into my specific examples, I do want to show quickly the recent SAT has started taking this idea on. I helped to write a workshop for the SAT on how to leverage the technology of the Nspire in 84, and we saw this problem a lot, where if x satisfies a certain equation, then what is 2x plus 1? And we know that a lot of students would probably say, well, I can solve that equation for x, which is not a nice number. I mean, students get a little intimidated when they see rational numbers that are not integers and fill that back in. In the end, we don't end up in a bad spot. But a student who understands the idea of simplifying equations, like we just saw in the Nspire, would maybe realize, oh, if I divide both sides by 3, I don't have to do anything now because I have 2x plus 1. And SAT has started asking that type of question, which I think is a great question, and it really challenges students to think about algebra, and it can be solved very quickly if you think about the structure of the equation. Okay, so when I'm teaching Algebra 1, I often tell students, hey, if we can simplify our equations down, let's do it, because we're going to end up in the same spot. And I know it seems simple, like the initial equation, 8x minus 16 equals 8 isn't so bad, but x minus 2 equals 1 is even better, and to look for that in their work. Okay, a couple more examples, and then I'll pass it off to Jan here. We saw this recently in Algebra 2. Okay, we were writing quadratic functions from tables. We look at things graphically, numerically, and algebraically in my class, so we're constantly looking at tables to see if we can write a function. Now my students would be looking for x-intercepts because they love to go to factored form first. Or can I spot the vertex in here? But unfortunately in this table, all we have is the y-intercept. So they had to start in standard form. And we talked about, well, now we have double the work because we need to find the quadratic coefficient and the linear coefficient, but we crafted our way into setting up a system by realizing, oh, if I take any 2 points from that table, I can create a system of equations. And then they kind of groan because they're like, oh, we did that in Algebra 1, why are we still doing that in Algebra 2? And I'm like, well, you're going to be still doing that in calculus, but so get used to it. But instead of going maybe the traditional route of something like substitution, and I'm just kind of clicking through this because that to me is the long way, you know, the long route on the GPS, what if we use this idea of simplifying our equations first? And we started talking about that and looking for that more. If we divide the top equation by 2 on each side, the bottom by 3, now we have a very simple system to solve if we subtract the equations using elimination. And they're at the point where if they see this, they're all over it. But if they don't do that initial step of simplifying, they don't catch that. And so we look for things like that. This one came up recently in a calculus test. My students had this function and they had to find the x value for the local minimum. They found their derivative, and this was a multiple choice question, and my students showed a lot of work, but some of them showed this. They were trying to factor this. There are a lot of factors of 120, and we just don't have time to be trying to sort all those out. And if you haven't practiced factoring with a lead coefficient that's not 1 in a while, this can be taking a lot of your time, and in calculus, time is of the essence, and we don't like to see that time ticking away. But for students who realized, oh, everybody's divisible by 3, now we factor, we can get to those critical values even quicker. So I want my students looking for that. So I push them from the very beginning of Algebra 1 into Algebra 2 and then into AP Calculus. So those are my 2 topics tonight. And again, it's all about that idea of equivalence, whether it's equivalent expressions or creating an equation that has equivalent solutions in a sense by simplifying them. To create some efficiency and then hopefully have them being a little bit more effective in their math. Okay, I'm going to pass it off here now to Jan. She's going to talk about some equivalent expressions involving exponents, as well as some very interesting things we talked about the other night involving composite functions. All right, so go ahead, Jan.
Thanks a lot, Scott. Let me get this sharing my screen. That was amazing, Scott. Thank you for all those helpful hints. I didn't know that the Nspire could do some of those things. I just want to start with thinking about our practices that not only that we think about in calculus, but we think about in all classes. And some of the practices we are hitting tonight is identifying a re-expression of mathematical information presented in a given representation, which was huge in Scott's, all of his factoring and redoing all those. Applying technology to develop claims and conjectures. That is not an assessed item on the AP exam, but boy, does that ever help when to help students learn through all that technology that we're using. I think my students, sometimes we are discussing things and they don't believe me. You know, they're wanting to go and, you know, challenge me, I should say. And so I get out the technology and say, let's look at this. Let's start exploring. All right. So my first topic that I want to talk about is rewriting radicals with a rational exponent. And I'll have to say a little bit about my experience this year is like Scott, I am now faced with teaching Algebra 1, Algebra 2, geometry, you know, pre-calculus as well as calculus. Can you believe that class load? But I am the high school teacher for an online curriculum. So I am seeing all of this again and thrilled to death that I get to be the one to teach them factoring, because I think factoring is like the biggest component that the students need to have throughout every course that they see in high school. And one of the things recently that I was talking about, it was, let's change these radicals to exponential form. And so students, so they're going through and they're like, well, that's really nice, but well, we don't believe you. You know, why is that true? Why is the cube root of 2x the same as 2x raised to the 1/3 power? We just can't see that. And that's the power of technology, is getting students to look at that. So, you know, we see this topic here, and I've lost my mouse. And we see this topic also when we're asking students to graph or describe a transformation. When they may be looking for a list of problems and they're seeing, oh, wow, look, I have y equal the square root of x plus 6, but what's that x minus 7 raised to the 1/2 power doing in there? And getting students to realize, hey, when you see that exponent of a 1/2, that is the same as the square root. That is comparing to the parent graph of that square root function. And so I'm looking here at asking my students to recognize and to be comfortable with these. And what I like to do is I like to throw some technology at them and say, okay, let's discover some things. I think I'm going to start on the 84. So let me pull that up. Can you see my 84, Scott?
Yes.
Okay. So I'm going to start with the 84, and this is what I would have my students do. I would say, okay, let's go ahead and let's graph the square root of 3x plus 2. And then let's go ahead and graph our parenthesis, our exponent of 3x plus 2. And I'm going to raise this to the 1/2 power. All right. I like going in and changing the way these graph. So I'm going to find it by going down to my line. I like calling it the circle with a tail. Okay, that's how I describe it to my students. Let's go look at that circle at a tail so we can see what's happening. Because I know it's going to be the same. The students don't know. And so I want to set them up for success on them. So then when I go to hit graph, I am seeing that second function, that y2, is showing up right there on top of that graph. And so they start to give me a little bit of credibility. They're like, okay, well, maybe you do know what you're talking about. Okay. And things like that. So if I go to, let's go to table. And this was probably my favorite feature. And Scott mentioned this earlier, that on the 84, you can see all your data right here. If I go back to my graph, and we can see, hey, these two are showing up the same. If I do go back to my graph, whoops, I went to table. If I go back to my graph and hit trace, I can see down at the bottom that I have the same X and Y values, but I have to go up here and toggle to get that Y2 and see, oh, look, both of those have the same Y value when I'm using the 84 trace. So this is why I like to use the table when I'm using my TI-84. Okay. Scott mentioned earlier about using the Y1 on the test, so I think I'm going to skip that. And I think that is all that I wanted to really do on the TI-84. I can do a split screen. Let's demonstrate that. If I go to mode, that is something we can do on a TI-84 if you would like to see the graph and the table at the same time. So then when I hit graph, there it is. Okay. So now in order to see all my data showing up, I again have to hit trace, and then I'm going to toggle up and down, and that's how I can get my data to show up. But again, I'm not seeing both of those at the same time. All right. So I'm going to go back to my mode. Again, that was switching to graph table just to make sure you understand that feature is there. We'll hit enter and get back on that. All right. Now, one thing I do want to mention is up here, Scott, he likes having things preloaded. I like coming in and resetting my emulator. Okay. So keep in mind that is a nice way to reset everything, but keep in mind that all your values for X and Y, all your stored values are going back to 0. And so that is something that you have to keep in mind. But as I'm going through and teaching it from class to class, it's nice to go and do that. Let me switch over to the Nspire. And I'm going to, I have already opened up a document. I like working in documents because I always tell students, if you work in documents, you can go back and look at what you've already done. So say you're on problem number 2 on your test and you're like, oh, that sparked something on problem number 1. If you're in Scratchpad, you might have already erased that graph. So you want to make sure that you already have this here and have access to it. So I'm going to type in my same equation that I had. So I'm going to type in my square root of, what was that, 3x plus 2 and didn't get an x value. 3x plus 2, and hit enter. And then I'm going to hit tab again, and then type in my rational exponent of 3x plus 2. And again, this is very similar of just taking some equations and seeing, do we have the same thing? But I wanted to show you a feature on the Nspire that is probably one of my favorite features when I'm comparing two equations like this. I can look at this and say, you know what, those are the same, but are they? So let's go over here to menu, and I like to trace when I have a couple functions graphed, trace all. So here I can look at this, hit arrow to the right, and look there at the bottom of the screen. We have our F1 and our F2 showing the ordered pairs. Okay, very nice for the students to see. I'm seeing both graphs. Sure, they're on top of each other. All right, and the other feature I'd like to look at is Control T, brings up that split screen. And I am not seeing both of those lists, so I can come over here if I can get my mouse to work, and I can stretch that. Of course, my mouse is not working really well right now. Come on, baby. There we go. So I can look at both of my functions here and see that the outputs for both of those functions are the same. Having the kids look at that numerically. Okay. So let's go back to my slideshow. So what is an activity that I like to do with my students? I like to challenge them to think about different ways that you can write your radical expression as a rational expression. And try and be creative. Don't just be obvious and write it as x squared plus 4 to the 1/2 power. How else could you write that? Okay, so think about this. Does this fit into your curriculum of helping kids realize how many ways can you rewrite one expression? How do we get this in an AP example? Well, we all know that when we go to find a derivative or a antiderivative, if we have a radical, we need to get rid of that radical. We have to do derivatives and antiderivatives with rational exponents. So I unfortunately picked examples that both were in the denominator, but obviously they don't have to be. We could have some in the numerator as well. Here is an example too of an AP problem where the students are working and they get, you know, they have the integral of 4x times the square root of x minus 1 dx, a little bit of, you know, a u substitution type problem. And this is a student produced answer. And my students would look at this and say, there's not an answer. A hand would go up during a test. There's not an answer there. And I'm like, are you sure? And students, hopefully, by the time, you know, they do get to calculus, they understand we need to have practice of converting this x minus 1 to the 3/2 power as a square root of x minus 1 cubed. All right. So in my classes, I like to give them, you know, give them a question where, you know, it's not calculus, but which one of these is equivalent to this answer over here? Or this is a student response and they're saying there's not an answer. Is there an answer? And which one would it be? Now, a lot of times students would say, well, I don't even need to know that because I look here and there's a 2/3. So most likely that's my answer. Okay, I get it. That's a good test taking skill. But let's, you know, maybe I would put one in, you know, a couple of them that would have a 2/3 in there for that. Okay. All right. So that's just a little bit of comparing radical expressions with rational exponents. What I really want to focus a little bit more on is composition of functions. And composition of functions, oh my goodness. My students, I give that to them and you would think I asked them to, you know, go run 3 miles or something. But it, you know, it's so many multiple steps that they get lost. And especially the first time they see a composite of functions. All right, so I am sitting there racking my brain teaching Algebra 2 for the first time with composite of functions going, wow. All right, we are really struggling here. What can we do? All right, so this is something I tried. I don't know if it's on the next screen or not. Yeah. Okay. So I looked at my students. I said, okay, let's think about this. I have f of x equal to x minus 2, and g of x is x squared minus 1. Can you give me g of 2? And they're like, oh, yeah, we can do that. You know, they're all over that. And I said, well, give me your answer. So they give me their answer. And I said, oh, can you find f of that number? And they're like, oh, yeah, we're all over that. But the minute I give them f of g of 2, they shut down. They shut down. And I said, now, come on, this is not, we can work this through. And they had a conceptual understanding of taking an input of g of x and taking that output, once you plugged in the 2, as the input of f of 2, or not f of 2, of f of whatever that is, and understanding that that is a composite function. All right, so let's look at, I think I want to do the 84 first. And let's try again. Okay, so on the 84, I reset this already. So I'm going to type in my x squared. Wait, let me think about this. What did I say my f of x was? I might get lost on that. My f of x was x minus 2, and my g of x was my x squared minus 1. So I always tell my students when I'm going to do this graphically, I want to put my inner function first. That's how I can keep it straight. So I'm going to type in my x squared, and then I'm going to type minus 1. So this is my inner function. This is my g of x. And then I'm going to type in my outer function, which is my x minus 2. Okay, so I'm just going to go and graph this. I'm going to use let's use a Zoom 4 screen. Let's see if that's going to do it for us. Okay. So this is what I would ask my students to do. I asked them to find g of 2 first. My inner function was my blue function. That's my y1. That's my x squared minus 1. When I hit a trace, I can say, okay, let's find out what do I get when I plug in 2? And I do this so we can do a lot of examples. And when I hit enter, I get my output is 3. They get that. I said, okay, now take that answer and plug it into my outer function. So I'm going to toggle down. I'm still in trace mode, so I can type in 3 and hit enter. My solution to that composite will be 1. So this is asking students to take the output from their inner function, and that becomes the input of the outer function. Now I'm going to go to table, and we can do this numerically using a table. Again, the students have to remember our y1 is our inner function. I wanted to plug in 2 to the inner function. Then I have 3 as my output. Now I take that output 3 and now use that as your input for your outer function. The nice thing that I like to do as well is once I go through this very simple example, they start to understand a little bit. Seeing it numerically, they understand that. So I'm going to go in then, I'm going to go back to my y equals, and I'm going to do a composite function. Now remember my outer function was y2, so I'm going to hit alpha, trace, here's my y2. My inner function is my y1. And then I'm going to put, I always like to, now you don't have to on the 84, but I like putting that x there just to make it look correct. All right. So I'm going to graph that and tell my students, okay, when I hit trace, look right there, my composite function, let's toggle up to it. My y3 is my composite function. Look what happens when I hit 2 and hit enter. I got that final answer right there. Okay. So that's trying to show them that multi-step process can be done as well as just plugging it into the composite function if it's been defined. Okay, so that's helping. And you know what? That worked for my students. It gave them a different avenue to look at. Okay, so let's go back. Sorry about that, hitting the wrong thing. All right, so here's the next thing I tried. As I said, okay, we have some more composite functions here, but I want you to create the composite functions. How are we doing on time? Okay, got about 5 minutes left. So we're going to create some composite functions and force students to see what can I use for my inner function? What can I use for that outer function? Because I found in calculus, if those students could know what a composite function looked like, boy, I was better off. So I'm trying all I can to get them to see that in a lower level class. All right, so I'm going to start with, we'll come back and play around with some of these others if we can. But I would challenge a student to say, okay, look at this fourth one down. What would you pull out to be the inner function? What would you pull out to be the outer function? And once they get it right, I'm just like, and they test it on technology, and I'm like, okay, now you have to come up with 2 more examples. So don't just give me the obvious. Here's what the obvious would be is the inner function is all this, and the outer function is just x to the 4th. Okay, that's too obvious. Give me something a little bit less obvious. So I challenge them to not give me just one answer, but give me 2 or 3. All right, so I'm going to work with this last one here because I think this is good in trig, getting students to look at this double angle formula as well as their graphing. All right, so I'm going to do the Nspire on this one. See if I go to my Nspire. Yeah. Okay, so I'm going to go home. I'm going to start a new document. Do I want to save this? No. Okay, so I'm going to add graphs. And here is how I train students to do this one. Remember, I want the inner function to be my F1. So I don't know what I want it to be. I'm just going to put X. It's going to graph. Fine. I'll come back and change that later. And then I'm going to hit my tab key. And now I want the outer function. Now, I'll be honest with you. My trig students, we're going to be doing this in a couple weeks, the double angle formula. And I'm going to have to give them what I want the outer function to be. So 2 sine, and I'm just going to put, now, I want this to resort back to my inner function. So I'm going to hit vars, and then notice that F1 comes up already. It's already defined. So I want them to see that, hey, I'm having the calculator tie in whatever I plug in for that first function. Now I'm going to hit control. No, I don't. I just want trig. I knew I was going to do that. So I hit trig, and now I'm ready for the cosine. And now I'm ready for my vars for the variables. And I want to have F1 there again. Okay, so I do train them on that I want that to come in. Now, I told my students that I wanted on this particular equation, I want my goal equation to be sine of x. And I might have glossed over that on my PowerPoint. But I told them what I wanted the goal equation to be. And our goal equation, I'm going to have to go back to tab, is sine of x. What can you do with those first 2 equations that I gave you so that the result is going to be my F3? Okay, now I'll be very honest with you. I'm going to hit tab, arrow up, and I'm going to turn off my F1 because that's just a little bit distracting. Okay, so in the chat room, what do you think your students would put in for F1 in order to try and get my final answer to be sine of x when it's finally reduced? So that's what my students would play around with. Do you have some thoughts on what your students would do when comparing my F2 to the F3? Well, for the sake of time here, I'm going to go in, my students would put a 2 there. Then I would graph that and they'd be like, wait a minute, that's not what I wanted it to do. That's what my students would do. All right. So then I would say, whoops, that didn't work. I need to stretch out the graph. So then I'm going to go up here and I'm going to say, okay, I want that inner function not to be x, but how about x divided by 2? Okay. Oh, bingo, there we go. So remember, my favorite feature is I'm going to go to trace and I'm going to do a trace all to quickly see, did I hit it? So I arrow to the right, arrow to the left. Then I'm seeing my values for y, and both my F2 and my F3 are the same. This is probably the only equation I would give my students the outer function. I would have them go back and say, let's go back to the PowerPoint slide. I would say, like on h of x, this is my goal equation. What two functions could produce that? Here I'm trying to get sine of x. My students wouldn't be able to come up with that if I didn't give them this part on this particular equation. Okay. And we all have different types of students, different level of students. And we lead them on how on how they need. I'm looking down here. Here's my Algebra 2 students where they have, give me two functions that could create x cubed. Give me two functions. With a composite, they could create that square root of x to the fourth plus 2x cubed. And again, leading them through having your F1 be your inner function, having your F2 be your outer function, and showing how to link those. Okay, so let's look at the tie-in with calculus. It is all about the chain rule. I tell you, my students, they look at that chain rule. I don't know about yours, but they kind of keep forgetting to take the derivative of the inner function. All right, so chain rule is all about composite functions. If my students in calculus could recognize right off, that's a composite function. What's my inner function? The inner function has to have its derivative. The outer function right here has to have its derivative. And so that's what I think about the important thing about composites by the time we get to calculus. And then, of course, use substitution is undoing the chain rule. So we have that being there as well. Okay. All right, Mike, I am ready to pass this off to you.
Awesome, Jan. And Scott, thanks so much.
Just a minute here. There we go, Mike. You're on.
Perfect. Thank you. As promised, one lucky winner is going to receive a TI graphing calculator. And tonight's lucky winner is Velvet Dow. So Velvet, congratulations. We'll be in touch over email in the next couple of days to get a little more information from you. But congratulations on receiving your TI graphing calculator of your choice. To receive a certificate of attendance, go ahead and click the link in the chat window. Also listed is a link for the documents for tonight. And Scott and I were talking before the webinar, and he mentioned that he's going to provide his PowerPoint to me after the webinar tonight because I know that there's some changes that he wanted to make. So the link that you're getting for the documents tonight will be really my documents. And then in the follow-up email in a couple of days, which will have a link to the recording, a link to the certificate, and a link to the documents, that documents link will be updated with Scott's PowerPoint as well. So be on the lookout for that, that follow-up email in a couple of days. And if you're watching this on demand, go ahead and copy down that link to receive your certificate. When you leave the webinar tonight, a brief survey will automatically appear in your browser. Your feedback guides us as we plan future online events, and we really hope you're sharing thoughts in the post-webinar survey. Huge thanks to Jan and Scott for everything you shared tonight. Thanks so much, guys.
Thank you so much for having us.
Hey, thanks for coming along, everybody, and hope you learned some new things about your technology.
Absolutely.
And thanks so much, everyone, for joining us. We hope to see you back online next week. Have a great night and stay safe.